Um, let's continue from last week. Welcome everyone. This will be Nikita's second talk in his mini course. We've got what were you planning for today in terms of what you want to cover?
So this time I came prepared by not preparing anything,
Okay.
almost just a few talking points. So I can't tell you. I can't answer your question. I'll just start talking, and then we'll see where that leads.
Okay, please, please share your screen and begin. Thank you. Maybe we can do a lightning review of what you talked about so far and move on.
Okay, so right. Okay, so last time the goal last time was to get to the statement of the main theorem, of the conjecture in the main theorem. So maybe I'll quickly restate that. So if you recall, my object, the thing that I'm studying, is a Schrödinger equation, which locally looks like this. So this is a local expression. And so the point was to look at what is called the WKB method to analyze so-called formal WKB solutions, which I will write in this form. Maybe like this. Maybe I'll call this phi hat h bar. So here, this exponential factor, exponential prefactor, involves an integral, which I'm calling s of x. So you would need to fix some base point, x naught, and it's the integral of the canonical one form, lambda. So I'm slightly mixing variables here. So, you know, I'm thinking of x naught as sort of base points on the original base curve, which I was calling x. But the canonical one form is something that's properly defined on the spectral curve. So the way to interpret this is that you have to, as part of the choices that you need to make in order to write down an expression like this, is that you need to choose a base point x naught, and you choose a lift, a pre-image of that base point to the spectral curve. Sorry, let me just rearrange my screens here a little. Right, right, and this phi is some power series in h bar with holomorphic or meromorphic, possibly multi-valued coefficients, which maybe right now I'll just call like this, phi of k. So meromorphic, multi-valued. So the conjecture, or the quantum resurgence conjecture that I stated last time, was that these are called formal WKB solutions, So formal, well, let me write it like this. So let x be P1 and D, the divisor, be just the point at infinity with some multiplicity. And Q, the Schrödinger potential, I'm going to assume that it's independent of h bar. So it only has this leading order part Q naught. And furthermore, I'm going to assume that it's a polynomial. It's a polynomial in X. With simple zeros. Then psi hat, these formal WKB solutions, are resurgent. That was the basic form of the statement. And what this means, and I'll get into this kind of explain or re-explain in more detail the meaning of this word in a few moments. But what this means essentially is that psi hat is Borel summable in almost every direction, and the directions in which it is not Borel summable, it exhibits a Stokes phenomenon, and the corresponding Stokes phenomenon is describable in terms of Borel resummation of other formal power series obtained, in particular obtained from the singularities. So let me just say, Borel resummation of singularity data. Of the Borel transform. So it's a very powerful property. And then the theorem, maybe I'll switch to the next slide, if that's okay. Actually, how come I can't, why does it, okay, never mind. I wanted to be able to show both slides at the same time, but that's okay, I can't. Anyway, so the theorem is that, so if you give me any marked curve, so any compact Riemann surface with divisor, and there's just kind of two basic assumptions, so such that one was about the degree of D, which is what is it? 2 minus 2g, g being the genus of X. So it's really only a constraint, more or less, on the case when x is p1. And then the other one is that I'll write it like this: poles of Q x h bar are no worse than poles of the leading order. So if there's a point on x where where some coefficient of this polynomial in h bar has a pole, then that is also necessarily a pole of q naught, and the order of that pole is no less. Sorry, the order of that pole is no higher than the order of the pole of q naught. So basically, the polar behavior is dominated in the leading order of h bar. And so then the conclusion is that then formal WKB solutions psi hat are resurgent, with just one caveat. So in all directions except those corresponding to divergent trajectories. Of the quadratic differential q naught of x dx squared. So in fact, I'll put this in brackets because I will not want to focus on this caveat. I want to kind of try to describe the essential reason why these formal WKB solutions are resurgent, and not worry about these. You could think of these situations as more or less freak cases. Although if you are considering a situation where you're just taking a compact Riemann surface X of, say, high enough genus, and D being, let's say, empty divisor, so that would fall under the remit of this theorem, then in fact this this behavior of having divergent trajectories of this quadratic differential would occur in many directions. So this would actually be a very prominent feature of those type of examples, and you have to deal with that in a certain way. But anyway, I will not speak about this. Does that make sense?
Yes.
Okay. Okay, so let me try to describe a little bit more in a kind of pictorial way what resurgence is about. What is the basic problem of resurgence? Basic problem of resurgence. So what is the input? The input is we have a formal power series, which let me maybe call it f hat. And let me just worry about one variable. Let me not worry about any kind of x dependence. We'll include that later. So for now, I just, you're just given some kind of formal power series, maybe like this. Which, let's say, comes to you as a formal solution of some sort of problem. And your goal is to take this formal solution and lift f hat to an actual solution, an exact solution, f So some kind of holomorphic function of h bar in a sector, perhaps. And so the way you do it is the way we're going to try to understand this is via Borel resummation. What does that mean? That means essentially what that really means is that you choose a direction, alpha, and you study the expression, which I will call f sub alpha of h bar, given by, okay, so there's the leading order part, f naught. At this point, it's just some kind of complex number, plus a Laplace transform in the direction alpha. So I'll write it like this: e to the minus t over h bar of phi of t dt. So the question is, this expression, is it well defined? If it's well defined, then this gives you a holomorphic function with various strong asymptotic properties, and in particular, it would satisfy whatever problem, differential equation, let's say, some differential equation that you're studying. This expression would satisfy it for as long as it is well defined.
What is phi?
Right. So I'm just about to get to that. Yeah.
Sure.
So here, could you go back? Yeah.
Yeah.
So what you're doing is you're saying that because I'm expecting my function f sub alpha to have a particular asymptotic smoothness in a particular sector, I would like to expand it out in terms of these Laplace transform components. You should think of it like a Fourier transform, where each component e to the t over h bar, e to the minus t1 over h bar, e to the minus t2 over h bar. These are all the different Fourier components. They're not Fourier components, they're Laplace components. And all these components, they behave well in a certain sector of the h bar plane. And the question is, what are the coefficients for all of these components that make up my f sub alpha? And those coefficients are the phi of t. Right? It's like a Fourier transform, but it's only valid in a particular sector in the h bar plane.
Yep. Yeah.
So actually, if you draw the contour that you're integrating along, which is, I guess, starting at 0 and going off to infinity in the alpha direction.
Yes, I mean that. Yeah, that's what I'm planning to do next. Exactly.
That's a direction in the t plane, and I think it would be good to see what sector is associated to that in the h bar plane.
Yes. Okay, so I've just copied that formula here for for reference. The other thing, let me just write down before I start drawing things. What is this phi? So phi of t is that's the Borel transform. That's what I mean by the Borel transform of f hat. The formula is very simple. You take you basically just divide all the coefficients by a k factorial, and you'd write that this gives you a new power series in an auxiliary variable t. Okay, from 0 to infinity. So in fact, here I will put a little hat over phi to signify that from as far as this formula is concerned, I'm really treating this as a formal power series in T, whereas in this formula, in this integral, what I'm doing is I'm hoping that this power series phi hat is convergent, so it gives me a holomorphic function defined locally near t equals to 0, and that I can furthermore analytically continue this function. So hence that's the origin of the difference in the notation. So phi hat is something very local to t equals to 0, and phi is its kind of global extension that we'll be talking about at length. So let me just write this Borel transform. Okay, so I basically kind of want to draw some pictures and go through a kind of a case study through several cases. So first case is, so imagine that there are no singularities. Is there a question? No. There are no singularities in the direction alpha. So if we draw this, so let's say here, this is a picture of the t-plane. Here is my origin, 0, and here is the direction alpha. So it's just a ray, infinite ray in the direction alpha. So what I'm assuming in this case, use blue, is that so a priori my power series phi hat is convergent in some small disk around t equals to 0, and then I study its analytic continuation along this ray, and I find that I'm able to analytically continue it to some kind of neighborhood, tubular neighborhood of this ray. So phi is the analytic continuation along alpha. If that happens, and furthermore, so there are no singularities, and let me add one more clause, and phi has exponential type, meaning that it is in some precise sense bounded, has at most exponential growth at infinity, so that this improper integral is convergent, well defined, then what you get is a holomorphic function f alpha defined on a sector at h bar equal to 0. So let's draw this. So here's my h bar plane. Here's my origin, 0, and which sector? So here is the direction alpha. So the sector has opening pi, so 180 degrees, and is bisected by the direction alpha. So if I draw a perpendicular thing here, then the domain of definition will be some kind of region like this. Maybe I can call it U. So to be absolutely precise, U would be of some form like this. So it's the point in the h bar plane such that 1 over h bar, the real part of 1 over h bar, is bigger than some real number r. So for some, and actually
Where does the alpha enter into that definition of U, though? Is it
Oh yeah, sorry, yeah. I forgot the phase. Thank you. It's e to the is it I alpha or minus I alpha? Minus I alpha. So basically, you want you want from the point of view of this expression, you want points on this ray have to be in this domain. So that you have to have phase e to the no, sorry, it's a plus. I always get this wrong.
This is not particularly crucial, but is the U rotated the other way by alpha? Like, is it really, is it, should it be like minus alpha in the H bar plane?
Okay, that's another thing that there are various ways to set up this convention. What convention do I have in this case? So we want, basically what we want is we want this exponential to be, we want it to be decaying to zero as t goes to infinity in the direction alpha.
Right.
So if t and h bar have the same phase, then this ratio t over h bar would be a positive real number, and so as t increases to infinity, then this thing will be overall negative, and this thing will decay. So I think t and h bar need to align in the phase. So I think this is correct. I think I'm rotating them correctly. And then this thing. So if h bar is on this ray and so that means it has phase alpha. So it's like some real number times e to the I alpha, and that would cancel with this e to the I alpha, and so I would get something real and positive. So I think this is correct. Does that make sense?
Yeah.
Right. Okay. Actually, in this picture, what is R? Even I can tell you, like this length, this radius. This is R.
Just to connect with what I was saying before, that if you fix this alpha direction and you look at this sector U, right? And if you're interested in functions which are asymptotically smoothly going to zero at the origin, right? Then these e to the minus constant over h bar for the constant being along that ray, those are a lot of such functions that have that behavior. So this is, you're kind of using these functions, e to the minus t over h bar for various different t. You're kind of using that as a basis in which to expand out the function that you're looking for.
Yeah, that's right.
So it's a sectorial form of Fourier transform, let's say.
Yeah. Okay, so I mean, so there's a huge amount of things that I could say about this. Maybe the only thing that I will say that is important is that let me say about the kind of the canonicity of this lift, this exact lift in the sector. How does it? What is so special about this particular way of lifting a formal power series in this sector? And the fact is that f alpha, this f alpha obtained by this this Laplace integral expression, is the unique holomorphic function on U with the asymptotic property let me write it like this, with the strong, so that there are many holomorphic functions which even in this sector which would have f hat, this formal power series that we started with, as an asymptotic expansion. There's a billion of them, but this one is the unique function with a very strong asymptotic property. So with the strong asymptotic property, which is that, I'll write it like this, f alpha of h bar, so it's asymptotic to f hat of h bar, as h bar goes to 0 in U. And I'll just write a few words and explain them verbally. So with factorial bounds uniformly in the direction of approach, so in argument h bar. Let me not get into the details of this, but what that means is that this f alpha, which is a holomorphic function in this sector, first of all, it admits an asymptotic expansion, so it's asymptotically smooth as you approach the boundary of this sector. This boundary being, well, in this picture, just one point. But if I think of it a bit more geometrically, then the boundary would be an arc of opening pi. So it'd be like a semicircular arc. That's the boundary of this sector. So as this holomorphic function, as h bar approaches this boundary, this holomorphic function admits an asymptotic expansion. That asymptotic expansion coincides with the given formal power series f hat. And not only that, the relationship between this holomorphic function and its asymptotic expansion is heavily constrained, in the sense that you could phrase it like this: the bounds on the what do you call it? The remainder. So the error, the error function, which measures the difference between the holomorphic function itself and its asymptotic expansion. That error function is bounded in a very strong sense. So that's what this factorial bounds condition corresponds to. And furthermore, that bound is uniform in how you approach the boundary of this sector. So it's a very strong property. Okay, makes sense? Any questions about this?
So I'm just wondering, so do you believe that it's possible to think about these functions, on such sectors? Should I think that the geometry of the sector determines a subsheaf of the holomorphic functions, of which this is like the unique member that
yes.
satisfies the condition.
Yeah.
So in a way, like what I'm wondering about is whether I can ignore all discussion of the formal power series and just beginning of this, take the first line of this slide and say, this is my ansatz. I'm going to look for solutions to my Schrödinger equation that have this form, that they are described, they're well defined on a sector, and they are Laplace transforms of such functions phi, right? And then you even go and identify the sheaf, the subsheaf in which you want it to live. Right, and then somehow the theorem is telling us that you will find a solution if you do this. Right?
Correct. Yeah, absolutely. That would be a good way to phrase it, and it's not in this paper, but in some other papers. That's how I've been trying to phrase this stuff.
Would the subsheaf be independent of the power series F hat?
The subsheaf. Can you? Sorry, I couldn't quite. Would the subsheaf be dependent on the power series F hat?
Or independent? Like, what would roughly
It would be. It would be more like you could you could just say. So yeah, you could just say you have a sheaf. So yeah, so here we're really talking about kind of sectorial germs. So the kind of radial size of U is really not important. It's the angular size of U which is crucial here. So so it's really a sheaf on the circle of the real oriented blow up. But anyway, you could say, okay, I have an algebra or a sheaf of holomorphic functions on sectorial neighborhoods. So that would in particular include functions which are holomorphic in sectors but do not admit an asymptotic expansion, right? They're blowing up as we approach the origin. That has a subsheaf of functions that do admit asymptotic expansions, and then that further has a subsheaf of there's a whole range of subsheaves that you could imagine, but in this case in particular you could say I'm looking at holomorphic functions which admit asymptotic expansions, and these asymptotic expansions have a particular regularity. So I wouldn't be fixing a particular formal power series, I would just be fixing a regularity class. Does that make sense?
Mm-hmm.
Yeah. And what this is saying is that if you take if you take local sections of this sheaf with a particular regularity class, then that sheaf is, you take local sections, you get an algebra, and then from that algebra you have the map of extracting asymptotic power series. And then what it's saying is that if you've imposed enough regularity and you've chosen a power series of corresponding regularity as well, then the preimage, the fiber of this asymptotic expansion map is a point. It's a single point which is then this holomorphic function, or the germ of this holomorphic function. Any other questions? So I always like to kind of liken this to something that we are familiar with, which is the interplay or the interchange that we do so naturally between holomorphic functions and their power series. A holomorphic function is in particular an analytic function, and so at a point it has its Taylor expansion, and there's an identification. There's a one-to-one identification between holomorphic functions defined on open little neighborhoods of a point and power series at that point, and we treat them. Once we understand this relation, we treat them completely interchangeably. When you get to these sectorial problems, that one-to-one correspondence, in a naive way, breaks down, but it can be restored if you impose more regularity assumptions on your functions, and this is really what's going on here. If I looked at the space of all homomorphic functions on on a sector of arbitrarily small radius, whatever, with the condition that they admit an asymptotic expansion, then I would not be able to identify. I would not have a one-to-one correspondence between asymptotic expansions and holomorphic functions. There's always many lifts. But if I restrict the space of functions where I'm testing this relationship by imposing regularity conditions, then it is possible to restrain yourself to a situation where you do recover this one-to-one correspondence. And so basically, from that point of view, a function with a certain regularity in a sector is the same thing as its asymptotic expansion. It's a slightly weird statement because one of these objects is a holomorphic function object, and another one is a formal power series object. But nevertheless, one could understand the equality, essentially, the identification between the two via this map, which is asymptotic expansion one way and Borel resummation the other way. I don't know if that's helpful. Shall I continue? Shall I continue? Okay. Okay, so second case is a kind of extension of the first. So suppose there are no singularities in the direction alpha for several alpha for alphas in some interval. So for all alpha in some interval, whatever, alpha minus to alpha plus, some interval. Open interval. So in other words, what I'm talking about is, again, let's draw a picture. I have the t-plane, I have the origin 0, and there are these kind of some sort of bounding directions, which I've called alpha plus and alpha minus. And so in all of these directions, alpha, I have no singularities. So that means that my germ phi hat, which initially is well defined in some little disk of t equals 0, that thing gets analytically continued to some kind of possibly tubular neighborhood of this sector, something like this. So here we have this function phi. So again, it's the analytic continuation. And again, I will suppose that it's of exponential type. So in all these directions alpha, it has some kind of exponentially bounded behavior. Then what? So just like in the first case study, so if in every one of these alpha directions, I will get a holomorphic function, which I've named f sub alpha. So now I have many holomorphic functions kind of indexed by this direction, alpha. And each one is defined in a sector of opening a pi, like of this semicircular sector. And as I rotate alpha, the semicircular sector rotates. And if I take the union of all these, I get this kind of a sector of bigger opening, in particular, pi plus whatever the length of this sector is. And because f alpha is defined by just an integral, just a contour integral in this in the t-plane, if I rotate, here, then you can just use what is the name of it? The Cauchy-Gaussat theorem, that if I change the contour, as long as the contour doesn't pass through any singularities, and I have an exponential bound at infinity, then the results of those two integrals will give me the same output. So the conclusion is that these this kind of collection, this family of holomorphic functions, they all patch together into a single holomorphic function. Maybe let me call it f sub a, a being this interval here. So f sub a, so it's a single holomorphic function on a sector with opening alpha minus pi over 2, alpha plus pi over 2. So let's, here's a drawing. So this is my h bar. This time maybe let me draw the circle, the blow up circle. And so if let's say this is my opening A, then this is the direction, whatever, alpha plus. so I would consider a sector of opening, semicircular opening bisected by alpha plus. So that would be like this. That's the circular arc bisected by alpha plus, and the same with alpha minus. So this is my alpha minus. That would be something like this, I guess. So the sector will look something, let me draw this again, something like this. Does that make sense?
Yeah, I think that's clear. Yeah. Okay, so next case.
Okay, so next case, case 3. So now suppose there is a singularity. Let's call it maybe psi in the t-plane in the direction alpha. So let's draw this. So here's my origin. Here's my ray alpha. And somewhere along this ray, there's a singular point, psi. And so that means that if I attempt, so a priori I have this little disk where phi hat is defined, gives me a holomorphic function on a little disk, and I start to attempt to construct its analytic continuation along this ray, I will succeed all the way up to psi, but not further, right? So I don't know how to draw this. I'll be able to do this, some neighborhood. Psi presents an obstruction, but if I assume now that this psi is it's an isolated singularity, so it's not a natural boundary, and so that means that there's a sense in which I could try to avoid it. I can go around it. So the kind of discreteness nature of the local discreteness of such points psi allows me to circumvent it. So that means I could modify my this contour along which I'm going to be analytically continuing phi hat, and there's two choices. I can either go left or go right, and then I can proceed all the way to infinity. And let's assume that once I've done this circumvention, I've circumvented this point, then no other obstructions are encountered. So I really just have this kind of picture. So then, therefore, I end up with two potential integration contours. Let me call them alpha L and alpha R. So although the straight Laplace transform is not well defined because the contour passes through a singular point, I may consider what I would call, people call it lateral Laplace transform. So in other words, I'm just studying this formula. So I'll denote the result F alpha, and I'll put an index L or R. And it's the exact same formula, but I'm going to be integrating. I'm just going to replace the straight ray in the direction alpha in the Laplace integral formula with this kind of distorted contour. E minus t over h bar phi of t dt.
So I'm sorry if I'm interfering with your future plans, but I think it's a good time to mention that, you know, when you circumvent on the left, or if you circumvent on the right, and once you've finished circumventing and you're now on the same path that you started with, it's important to realize that you're not actually on the same locations. You're actually working on, a covering of your original surface, and the continuations of those paths. They are in different locations. And so you have to make two separate assumptions. You have to assume that the function is of exponential type on alpha L after the singularity has been circumvented. And you have to assume that alpha R, that the function is also of exponential type for that analytic continuation. And when you look at this integral formula, the phi of t, those are two different phi's of t's, depending on whether you're taking the alpha L path or the alpha R path. Right? Because you're really working on the analytic continuation Riemann surface.
Yeah, all of that is absolutely right. Maybe to make this, that was indeed the next thing I was going to talk about. So what we need to realize is that this singularity, this singularity could be a pole of phi, in which case, we just have a meromorphic function and it's well defined in a punctured neighborhood, no monodromy. But in general, this singularity could be of branch point type. So it could be, for instance, a logarithmic singularity. So that means that this function phi of t, even though I'm writing it like this as a function of t, it's actually a multi-valued function on the punctured neighborhood of psi, like a logarithm would be. And so that means that indeed, just as Marco just explained, when I do this process of circumventing the singularity, or on the left or on the right, that means that I am continuing this blue contour on two different sheets of some Riemann surface, which is sitting above the t-plane. So what I should do is I should draw perhaps a branch cut emanating from psi. So now I've told you which branch I'm selecting of this multi-valued function. And then I need to make it clear that the two legs of this infinite contour, they are sitting on two different sheets of this Riemann surface. Yeah. And so, okay, so the point is that this defines, but both of these define two holomorphic functions on again on a sector, on the same sector U. So this U, let me just draw it. It's this kind of half plane sector bisected by alpha. This was U. This is alpha. So let me make a, oh yeah, right. And so let me make a point, kind of make an analogy. Sorry, let me just scroll back to 2 slides before, just remind you of this fact that I mentioned. So the kind of the really important property of Borel resummation when F alpha is defined by this straight Laplace transform is that the resulting holomorphic function is the unique holomorphic function which is asymptotic to F hat in this sector U. And it's the unique one with these strong asymptotic properties. And I now contrast this with this situation where I've obtained 2 holomorphic functions defined in the same sector U, and they both satisfy the asymptotic condition that they are asymptotic to this power series. So this is as h bar goes to 0 in U. And this is not in contradiction with the previous fact, because although these asymptotic expansions have factorial bounds, they are not uniform with respect to the direction of approach.
So both of them blow up as they approach alpha?
As they approach the alpha plus pi over 2 or alpha minus pi over 2. The bounds, these factorial bounds would blow up, yes. So yeah, let me just kind of circle this in red and say, therefore, this fact is not in contradiction with the uniqueness in previous fact. This is it seems like a very subtle point, but it's important. So in other words, because I don't have this, another way to kind of to draw this observation, because I'm missing this important uniformity condition, that means I simply cannot conclude that the 2 resummations, these lateral resummations left and right, that these 2 functions are actually equal. And in general, they're not. So F alpha L does not equal to F alpha R. And so this is the kind of, this is the nature of the Stokes phenomenon. In resurgence. Meaning that we have a single object, F hat, and we have a single method, kind of a single machine that takes F hat as input, takes the direction alpha as input, and outputs the holomorphic function. And as alpha varies, the output is consistent. Like in the second case study, I mentioned that if there are no singularities, then kind of all these nearby resummations, they glue into the same holomorphic function. So you could think that the output of this algorithm is constant, kind of constant with respect to alpha. But there are singular directions where you encounter singularities, at which point, although the input is the same, the output has a discontinuous jump. So that's the Stokes phenomenon in this business. Does that make sense?
Yes. So at this point, are you going to discuss the difference between them? And
that's what I was going to do. Yes.
Yeah, please go ahead.
Okay. So right. So we could try to indeed understand, like, these two functions are not the same. So how do they differ? How can I describe this difference? You could say, one way you could say why this could be important or useful, and this is actually very much an approach that permeates a lot of mathematical physics, which is that in many of these problems, it turns out that constructing Borel resummation of a certain power series that you encounter in your analysis of some kind of model or whatever, a certain power series is very easy to Borel resum in some certain direction or some kind of certain sector of directions. There's a kind of obvious answer or something like that. But then in other sectors, it is very much not the case. It is very much not easy to guess or analyze the resummation. But if you could approach this problem through kind of understanding the Stokes phenomenon, which is that if you can understand resummation of your object in one sector, and you can understand the jumps, these discontinuous jumps across these rays, then the way you could construct the answer to the problem that you require is you start with the resummation that you understand very well, and then account for the Stokes jumps in an appropriate sequence, and that would take you to the sector that you actually are interested in. So that's one way you could describe that. So here, what I've written on this slide, this difference is trying to understand that question. What is the jump? How can I understand this jump between the two possible resummations? Well, okay, so let's write. Let me draw that picture again. So this was the origin. I had this ray alpha. There was a singular point at psi, and I had these two contours. Like this. So I call them alpha L and alpha R. So if I just write down the formula, what do I get? So I get the integral along alpha L of e to the minus t over h bar phi of t dt minus the right contour like this. So, another way I could try to understand this is just basically the integrand in these integrals. That's the same multi-valued, but it's the same function. So if I'm treating these contours on the appropriate Riemann surface, then the integrands in these integrals are literally equal. So that means I can combine the contours into one contour, so just concatenate and integrate whatever it is that I'm integrating. So now that means now I need to try and understand what this concatenated contour is. So what is meant here by alpha L minus alpha R is that I'm first going to follow alpha R, but in the opposite direction, so with a minus. So I'm going to go from infinity to 0. And then I'm going to concatenate it with alpha L and go back to infinity, but along this contour. So that means I'm doing this kind of this kind of loop based at infinity. And so immediately one thing that we can notice is because because the branch cut, I'm choosing the branch cut to go off from psi off to infinity like this. The values of the integrand, I mean, they really just depend on the values of this function phi, holomorphic function phi. But these values along this part of the contour here, they're equal. It's the same function, but I'm integrating it in opposite direction. So that means, in particular, I can just remove this part of the contour and just focus on this keyhole contour. So let's draw that. So let's call this perhaps beta, combined contour beta. Okay, so what we really have is the integral along beta of e to the minus t over h bar phi of t dt. And here I'm being slightly imprecise because I'm just writing, I'm writing phi of t as if it were a univalued function of t. So what I really should write is I could write it like this. I really should take this contour beta and break it up into two parts. One which goes from infinity to psi on one sheet of the Riemann surface, and one which goes from psi to infinity, but on the other sheet. So let me write it like this: psi to e to the I alpha infinity. I'll write it like this. Phi, and maybe I'll write it. I'll indicate it. I'll indicate the kind of which branch of this Riemann surface I'm talking about by including a little index here, L or R. Like this. E to the I alpha times infinity, e to the minus t over h bar phi of t r dt. Okay, let me combine this again. In a slightly different way. I mean, just combine the integrand. So you have this expression phi of TL minus phi of TR dt. And so what I notice from this is that what's really going on in this integral is that I'm just taking a single contour, just a ray in the infinite ray in the direction alpha, but emanating from psi, not 0. And the thing that I'm integrating along that ray is the difference, or like the discontinuity of my multi-valued function along the branch cut. And if I look at this contour again, so as I said, it's just an infinite ray in the direction alpha, but starting not at 0, but at psi. So this integral almost looks like a Laplace integral, Laplace transform of whatever this holomorphic or multi-valued function is. It's almost like the Laplace integral, with the only exception that the Laplace integral starts from 0. The contour in the Laplace integral starts from 0, not at some non-zero point psi. But we can easily adjust by shifting the integration variable by psi. So I'll go to the next slide. Sorry that I can't show them both at the same time. So if we take t and replace it with psi plus t, then this integral, let me just copy it here so you have it in front of you. T over h bar phi of TL minus phi of TR dt. This thing becomes, so you have this, I'll just write it like, use the notation that I used before, just the integral along this infinite ray alpha of e to the t over h bar times e to the minus psi over h bar. So that's the thing that popped out because I've shifted my integration variable, times what I will now call maybe delta psi phi of t dt. So this delta psi phi of t is just it's just the discontinuity. So discontinuity at the given singular point. Like this. Discontinuity of phi at psi. Okay, and let me just make one last thing. So I'll just take this exponential prefactor out, e to the minus psi over h bar times, and I'll write the rest as the Laplace transform in the direction alpha of this function delta psi phi. Right, and so on the left-hand side of this was f alpha L h bar minus f alpha R h bar. And so what we've done in this rather simple calculation is we've expressed the jump in Borel resummation, this discontinuous change from left lateral resummation to right lateral resummation in the face of a singularity. We've expressed it in terms of Borel resummation of another holomorphic object in the Borel space, which is the discontinuity or the data at the singular point psi of the Borel transform. And this thing is a function of h bar, and importantly, it has this exponential prefactor. So in particular, you can see that if I try to take the asymptotic expansion of this expression, because of this exponential prefactor, the asymptotic expansion of this term is 0, because it's exponentially what do you call it? It's a sub-exponential. Yeah, it has sub-exponential behavior. So if you construct the asymptotic expansion of this, all the coefficients will be 0, and the limit as h bar goes to 0. So so in this expression, you can clearly see that the two Borel resummations, left and right, two lateral resummations, they indeed have the same asymptotic expansion. So from the point of view of asymptotic series, you would not be able to detect the difference between these two functions. They have the same asymptotics. But they're not the same functions, and the Stokes jump is given in terms of this sub-exponential term.
Can I ask a question?
Yeah. Mm-hmm.
What happens if phi had a pole at xi?
Yeah. So if phi has a pole at xi, yeah, let's go back to this picture. Indeed. So I would then be able to just not draw this branch cut because it's a single valued function. And if I think about this part of the integration contour, this and this, I would be integrating the same holomorphic function along this contour, but in two opposite directions. So they will cancel. The only thing that does not cancel a priori is this loop around the pole. And so then, sorry?
Well, yeah, go on.
Yeah, so then you can see that this difference really just amounts to, I mean, this is a residue contour, right? You're just computing a residue. So in particular, if you have, you could have, if there is no residue but a higher order pole, then the two lateral resummations would agree, even though there is a singularity on the contour. So that would be like a trivial jump. There is no jump. It's just the residue that would contribute to the discontinuous jump.
But I guess I meant like if it could have both a logarithmic singularity and say a residue, like a pole of order one, like how, or even a higher order pole, how would you write that formula, like the L of the, because you're integrating out of the pole, and I was just wondering how would that?
Yeah, so that's a very good question, actually. In this discussion, the fact that when I jumped from this expression to this expression, where I said that we can forget about this part of the contour, I made a certain assumption about the behavior of phi at the singularity. Let me just leave it at that. There's in my discussion, there's a hidden assumption that kind of contracting this loop to an infinitely small loop so that I can actually treat this contour as a straight line ray emanating from psi, that requires an assumption about the behavior of phi at its singularities.
Okay, so you would need to include both types of singularities and treat them separately, and you would get two types of terms, one of the residue term and one like this. So I just have a question about this. So could you go to the next slide? So here you're giving an expression that measures the difference between the two resummations that derive from the fact that there's a singularity in the Borel length. Now, in the resurgence conjecture, in saying that that WKB solutions are resurgent, this involved, part of the meaning of resurgence is that the two lateral resummations should be controlled in some sense, right? And so, so somehow this red box is part of the resurgence phenomenon. And
yes.
So, like, how should I think of, if I think that I started with a power series, I manipulated the power series, and I analytically continued it, and I Laplace transformed it to get these F sub alphas. And now you're telling me that the difference between the two solutions on the left and the right is the Laplace transform of some other function. Is there some claim about that other function being itself the Borel transform of some other power series that I could have in the first place, that is somehow related to my original power series?
So that turns out to be the case. It's not really part of the conjecture. I mean, it's certainly not any property like this is certainly not claimed by a Cal. It is possible that that relationship is implicit in what Voros discusses in his paper, but not explicitly. But this relationship is, so there's this paper by Delabert, Dilliger, and Pham. That's where they explore, they basically, their paper is, they assume that, their work basically can be summarized like this. They assume that the formal WKB solutions are resurgent, and then they try to understand these jumps more explicitly in terms of integrals along contours around turning points. And so the conclusion there is indeed this Xi, in particular this Xi can be understood precisely, and this power series can be understood as a, well, they give a more detailed description of what this jump is in terms of the formal WKB solutions themselves.
Okay.
Yeah, is that okay?
Yeah, that's fine. Yeah.
Okay, right. Okay, let me just very quickly discuss kind of a fourth case, which hopefully will suggest why it's the full global nature of the geometry of the Borel transform that needs to be understood, not just kind of these rays and slight distortions of them. So suppose, so case 4 is, suppose there are many singularities in a given direction alpha. So let's draw this. So here is the direction alpha, and let's say there's 2 singularities, just to make it simpler. Then again, I can do, if I try to Borel resum f hat in the direction alpha, I will fail. But if I distort the Laplace contour, I can distort it by circumventing these singularities both on the left or both on the right, and I will end up with a kind of an admissible contour. And then if the exponential type at infinity, if I have that property, then the 2 lateral resummations will result in 2 functions. So here again, I have alpha L and alpha R. So F alpha L, F alpha R. Again, I have 2 homomorphic functions, on the same sector U that I've been calling U. And once again, I have this phenomenon that these 2 lateral resummations, they are not the same. So I can ask, what is the difference? What is how do I compute the jump? So let me draw this picture again. So we have 0. Here is my ray alpha. I have 2 singular points, Xi1 and Xi2. And recall, when I'm now kind of trying to deform these contours, etc., I'm really deforming them on this Riemann surface. So in order to picture this Riemann surface, I need to choose branch cuts. And now this time I have 2 branch points, 2 separate branch points. So I'll have 2 branch cuts emanating. So I'll draw one like this, and then maybe I'll draw the other one like this, just to avoid, just so that they're not coinciding. You could say, what if I connect the 2 things with a branch cut? That's, I may not be able to do that because that may not be the structure of this Riemann surface. Like if these are two logarithmic singularities, there's no way I can connect them with a branch cut like that. So that means that when I'm considering this contour alpha L minus alpha R, what I'm doing is I'm doing some kind of contour like this. So this is my alpha L minus alpha R. And then the next thing was, what I did was I deformed it even more into this keyhole contour, which I've called beta. Now let me now use a different color just to make it stand out at beta. Yeah, so let me say it in words first. So if I want to present this difference of contours as a keyhole contour, it would be a keyhole for each singular point. But here's a kind of a tricky thing, that because I have these branch cuts, the two keyholes would be starting and ending on different sheets of the Riemann surface. So I have to be careful about how I draw it. So I have one keyhole like this. I will call that maybe beta 2. And then I have another keyhole which goes around like this, around the singular point and back to infinity. Now we'll call this one maybe beta 1. And so the way I can understand this difference now is by, I have a sum now over each of the keyholes. I have so a sum integral of e to the minus t over h bar phi dt plus another keyhole beta 2 e to the minus t over h bar phi dt. And so the fact that these keyholes, so like focus on these two legs of the two keyholes, keyhole contours that I have. These two legs, they belong to a sheet of the Riemann surface, which is neither, to the left of both cuts or to the right of both cuts. It's a kind of intermediate, it's genuinely a kind of a third previously unseen sheet of this Riemann surface that I have to bring into play in order to understand the behavior of these jumps. So, yeah, you could maybe say it in words that so it's not enough to understand phi on just the first sheet. So like in the previous case, in case 3, you could suspect that you could get away with that if you could just understand phi on just the one sheet, because I'm integrating on both sides of just one branch cut. Then I would be able to tell you what the jumps are and singularities, etc. But as soon as you have a situation like this where you have more singularities than one, it is no longer possible to just be content with the information on the first sheet. You need, sometimes in the literature on Resurgence, they say it kind of understanding slightly beyond the first sheet. That's what. So this is the kind of behavior that they mean. But of course, what that really means is, if you need to understand slightly beyond the first sheet, you might as well try to induce some kind of geometric picture of what's going on and understand the whole Riemann surface, all the sheets. So, so this kind of brings you to the idea of constructing or analyzing endless analytic continuation. So endless analytic continuation is a property. And this property just means that the Riemann surface of phi hat has, the way I phrase it is, it has only isolated singularities. There could be infinitely many of them, but they always have isolated singularities. And the upshot of this this kind of locally discrete nature of singularities, the fact that they're isolated, is the fact that if you know that a given singularity is isolated, that means you can always circumvent it on the left or on the right and then proceed.
Just a quick question. If there's infinitely many things along this array, then we're going to be performing, like we'll have beta 1, beta 2, beta 3, whatever, and we'll get some sort of infinite sum here. Is that going to create issues for us?
It could, yeah, it could. You could perfectly well ask. Indeed, you would have, you could have some kind of infinite sum of these kind of keyhole contours, something like that.
Yeah.
And you could well ask, does this infinite sum converge? And in general, that may not be the case. But in the case of these kind of this resurgence property, if part of the quality of being resurgent means that even if you have infinitely many singularities like this, the two lateral resummations, so in this case the L and the R, those two resummations actually exist. They give you holomorphic functions. So that means this difference would be a well-defined holomorphic object in H bar. And so that means that even if the Stokes jump between these two holomorphic functions is some kind of infinite sum, just from this equality, you can conclude that this sum would be convergent.
Okay. Yeah, makes sense.
Mm-hmm. So what time did we? I mean, how much time do I have? I don't know what time we started.
We have 10 minutes. So I'm not sure. What was your plan?
Well, next I wanted to turn to the Riccati equation and explain how, what are the geometric ingredients in order to construct this Riemann surface, or the family of these Riemann surfaces. But that cannot be done in 10 minutes.
It's because of the lack of time. Maybe it would be good for you to just, given what you've been explaining in detail, which is for a fixed x, or in other words, x is not in the picture. Can you just kind of point out what the result says, in the sense that, it's telling us in the actual application that you're using this in, it's telling us what this Riemann surface is, where the singular points lie. So just give us that information so that we can integrate.
Okay. Yeah. So the theorem says the following: that for every point P in the Riemann surface sigma, so this was the spectral curve, for every point P which is not a pole nor a ramification point, this the Borel transform of phi hat at P H bar. So here I have P is fixed, so this is genuinely a power series in H bar. This Borel transform phi hat, which I don't know what to call it. Well, let me call it little phi hat p t. So this is a priori a power series in T. But the first kind of easy claim is that this is actually a convergent power series. So it's in this subalgebra. So this phi hat defines or extends naturally to a Riemann surface which, let me maybe give it a name, maybe sigma tilde p for now. Riemann surface sigma tilde p with isolated singularities. And exponential type. At infinity. And so what is this, this sigma tilde p? This is, it's the universal cover of the spectral curve, sigma, punctured along the poles, which I was denoting by delta, based at p. Oh, sorry, let me, I missed maybe one important thing. So I said extends naturally. At this point, let me say it extends naturally to here, to a multi-valued holomorphic function. On this universal cover, what are the singularities? The singularities which I'll call the subset to be gamma sub p. So it's a subset. So you need to think of the universal cover as these are homotopy classes of paths on sigma without delta, starting at p.
Can you recall what is delta?
Delta was it's basically just a preimage of poles. So we have the Schrödinger equation on this marked curve x comma d. That gives me the spectral curve. Pi is the projection from the spectral curve to x, and I just take the poles and pull it back. Now, okay, I also have to remove 2 times the divisor, but let me just assume that whatever the branch points and the poles are separate, so I don't have to worry about this. So homotopy classes of paths on this punctured spectral curve, sigma minus delta, starting at p. That's what this that's how I'll think of the universal cover based at p. And then from this point of view, it's easy to say what this subset of singularities is, gamma sub p. So gamma sub p is paths that terminate at a ramification point. So in other words, it's yeah, it's the target preimage of the ramification divisor. So I call these critical paths. So what I'm saying, yeah, okay. So what I'm saying in this sentence is that this phi hat extends to a multi-valued function, holomorphic function on sigma tilde p punctured along the critical paths. And so in fact, you can describe you can describe the actual Riemann surface where phi hat defines a global holomorphic function. So in fact, phi hat extends to a multi-valued holomorphic function, and we call it phi. Sorry, phi without the hat. In fact, phi. So phi is a holomorphic function on. Now I'll get in trouble. Let me use this notation. So sigma p tilde star. Tilde goes kind of over both of them. So this is the universal cover of sigma punctured not just along the poles, but also along the ramification points based at P. So literally, phi is a global holomorphic function on here. And maybe I should, in the notation, maybe I should like put like maybe sub as an index sub p, just to indicate that here I'm kind of keeping p fixed like this, and so that the next part of the statement of the theorem is how these Riemann surfaces evolve as I change p, and so they actually assemble into a fibration over this spectral curve, and this extension, this analytic continuation phi without the hat, which is now a function of p and t, or yeah, that extends to a global holomorphic function on some two-dimensional holomorphic manifold.
So just since we're we are out of time, but I just want one last piece of information which kind of connects the first part of today's talk and the second part, which is that this analytic continuation that you're doing, you're saying that that analytic continuation eventually will construct these surfaces that you're listing on this page. And so the last piece of information we need is what's the relationship between sigma tilde p and Borel plane. So there's a map, right, that you define from one to the other.
Right. Yeah. Sorry, let me just write it on the next slide. Yeah. So there is a map, a holomorphic surjective map, submersion, in fact, which I call central charge. And so let me just write it on one of these Riemann surfaces, sigma p tilde to C, and this C is the T plane. That's the Borel plane. And all it does is it takes a point in this Riemann surface, which, as I said, is the universal cover of which you should think as homotopy classes of paths that start at P. So I'll literally use the notation gamma for points in this Riemann surface. And all you do is you integrate along gamma the canonical one form lambda. Well, okay, caveat, non-caveat, details. There's a 2 for a good reason, but never mind that. And this is your point T. And so kind of cool fact is that ZP is it's an infinitely sheeted cover, infinitely sheeted covering. No, sorry, that's not. It's not necessarily infinitely sheeted. It's so this is it's a holomorphic submersion away from exactly the locus of critical paths. In other words, these are the ramification points of Z sub P. This is why I chose the name critical paths. They are critical points for Z sub P. And yeah, and all of them are, therefore you should think of them as algebraic singularities. And so, yeah, maybe one thing, the reason I stopped short of writing that this is an infinitely sheeted covering is that although, because this is a ramification locus, it's necessarily discrete, and so this has this kind of isolated singularity feature that I mentioned as part of Resurgence. The image in the T-plane of this subset, so the subset of singular values of this map could have accumulation points. In fact, it could be everywhere dense. It could be that poorly behaved. Okay, I think maybe that's enough.
Will there be a round 3?
Sorry?
Will there be a round 3?
Oh yeah, I don't know. It's
We'll try. Right now we have other talks planned, but we'll try sometime in the next 2 months. Yeah. Any questions? Okay, thanks, Nikita, for this and your first talk.
Thanks.